we were saying that we have defined the loads that go onto the wall. Say there's soil, there's water, and there's the surcharge, or what is the other name? Overburden that we have put onto this wall. So now we need to proceed and calculate the bending moments that would go into this wall, courtesy of those loads. The bending moments that this wall would generate, courtesy of these loads. Sorry, just a moment. So let's write here bending moments, resulting bending moments, resulting bending moments. So again, let me sketch the wall. Let me sketch the wall here. That line. So you remember that the height of the wall we're trying to design is 5 meters. So this value here will be 5 meters. For now, 5 meters. We'll write that with a pen. This is 4 meters. 5 meters, 5 meters. There's a number that is not right. We'll go back to correct it. Sorry, ladies and gentlemen. I think my day has started with too many things. So that's 5 meters, and this is 4 meters. Please allow me to correct this number. Allow me to correct this number. It's not 5, it's 5.4. You guys are not telling me. Now that we've decided to take the loading from the bottom here, this number is 5.4. 5.4. Yeah, 5.4. So this value will change a bit to 54. The value will be 54. This value will change a bit to 6 by 5.4. 32.4. This number will change to 32.4. Sorry about that. This number will change to 32.4 kilonewtons per meter square. Please be checking these numbers as we go along. As probably I might have mentioned to you that as structural engineers, we are notorious for making very silly mistakes, like this one and the one I made in the previous worked example, which we have corrected in this calculation. So please be checking these numbers, ensure that they make sense to you. So again, we start with water. We had drawn the thing for, or we start with the soil. Let's start with the soil. So we want to draw the bending moment that would result from the loading courtesy of the soil. Bad line. in here as well. Okay, so yeah, that's better. So this being a cantilever, just to remind you of some bit of analysis of structures. Space here? No, it's here. So say the side. Cantilever with a UDL, cantilever, lever with a UDL. Just to remind you, this one I know you know. And it has uniformly distributed load. The bending moment will look like this. It will be a parabola like that. Not a good line. Okay. A parabola like that. Yeah, that's better. And this value here will be simply WL squared over 2. This is cantilever with a uniformly distributed load. Now, when we have a cantilever with a uniformly varying load, the equation changes slightly. So we have a cantilever. We draw it a bit lower here. With the cantilever, if the loading is a triangle like that, so it increases linearly, like what we have for this wall. Okay. The bending moment diagram is still a parabolic bending moment. The variation is still parabolic, but the number changes a bit. The equation changes a bit. Again, I'm saying this is something that you have done probably in some of your units for analysis of structures. So this equation becomes WL squared over 6. WL squared over 6. Okay. Get bending moment diagram. BMD here. BMD. So we'll use these two equations. We'll use the one with the UDL for this loading, courtesy of the surcharge, and then we will use the one for the UVL for the soil and the water. So we start with the soil. Start with the soil. The first loading we've calculated was for the soil, so we start with the soil. We draw the bending moment diagram. We know that it will be parabolic like that, and this value here will be WL squared over 6. WL squared over 6. What is W? W is this value here. Is this value here, 32.4. What is L? L is 5.4. So we have 5.4 squared. We divide this by 6. What's the value? What's the number? So we have 157. Please be confirming these numbers as we go along so that we avoid the silly mistakes that you can see I am making here. So this will be kilonewton meters per meter. Now, I'll remind you this concept of per meter so that we doesn't look like it's a weird. I want to stop sharing briefly to just explain this thought of kilonewton meters per meter. Now, okay. So I want us to look at this wall here. This wall here. It's a long wall, many meters. And the arc is pushing this wall. We have two options. We could design the whole length of the wall, or we could take a strip of the wall and design it. And use that design for the whole wall. Apply it for the whole wall. It's the same concept that we use for slabs. We have a slab. We have a slab, and this slab could be 30 meters. But we take one strip of 1 meter width, and we design that one. We calculate the loading for that one, we design that one, and then that design, we simply replicate it or duplicate it for the entire length of slab. So it's the same thing with the wall. The whole wall is feeling some pressure, which we have calculated. We want to take 1 meter width strip. We load that one, we analyze that one, we design that one. Then we apply that design, we replicate it for the whole length of wall. So if the wall is 1 kilometer long, we don't need to design 1 kilometer long wall. We just design a meter width strip, and then we say, so this whole wall, for every meter width, we need to provide this kind of thing. Let me share this window again, where we were. Okay, I will. I'll explain a little bit better this concept of the meter width when we probably in the next session, because we've not finished this session. We'll finish it in the next session. So I'll explain this a little bit better in the next session. But that's the thought, that we want to load 1 meter width strip of the wall. We want to design, to analyze that, design that, and then just replicate whatever specification we found for the entire length of wall, just the way we do for slabs. Okay. So we found the loading bending moment diagram for the retained earth, okay, soil. So we'll label it here, soil. Similarly, we draw the bending moment diagram for the water. draw the bending moment diagram that will be generated courtesy of the force that the water will be pushing this wall with. So do that. Let's use the same color. So here again, we will have a parabolic, and this will be similarly WL squared over 6. So this will be, what was the value we calculated? 54. Sorry. 54 multiplied by 5.4 squared over 6. So again, we have 5.4. This will be 262, say 0.4. Again, kilonewton meters per meter means every meter width strip of that wall is carrying, it has to carry 262.4 kilonewton meters courtesy of the water that is retained by that wall. Okay, should wind up shortly. Then we now come again and calculate the bending moments on this cantilever courtesy of this surcharge. We are being a bit generous. Maybe I will not go into the detail of why I'm saying that, but we are being a bit conservative in this calculation. Maybe later on I will highlight that, but it's important to just note that we're being a bit conservative. Maybe I can mention it. You know, the wall, if it was to fail, it would fail there from our previous discussion. But we are calculating a moment that is further down here, is bigger. Ideally, the moment we should calculate for the wall is here. So we are being a bit conservative because we are calculating a slightly bigger moment than what will actually exist in the beam. Again, this is just it would be your call as the designer to say that what exactly you want to work with. Whether you want to work with the exact value where the wall is likely to fail, or you want to be a bit generous, again, it will be your call if you were to do this design. So now for this one, because it's a uniformly distributed load, we will work with WL squared over 2. Okay, so the moment here will be WL squared over 2. So what is W? We come back here and pick value of W is 7. So pick 7. L squared, so 5.4 squared over 2. So say 5.4 by 5.4 by 7 by 2, 102.1, 102.1 kilonewton meters per meter. So what we have done is we have calculated first the loads on the wall, the loading on the wall. Then we have gone ahead to now calculate the bending moments that are resulting from those loads on the wall. Bending moments that are resulting from those loads on the wall. Just to remind you, we said, what about the process of design? We said you start with the structure or structural element. You load, and by analysis of structures or theory of structures, you find member forces. Okay, so what we have done is we have done these two steps. We've loaded, and by analysis of structures, we have calculated the member forces. Okay. What is left is to now run the design to decide how much reinforcement we need to put into this wall to be able to carry these forces. And I'm suggesting that we do this in the next session so that you digest what we have discussed today. We'll finish this in the next session and maybe discuss something else in that session as well. I want to allow you, if somebody has a question or a thought that you'd like to share, please, you can go ahead and do that before we wind up this session. Any question, any comment?
Yes, excuse me, sir.
Yes, John.
You said that it will be much safer working with the maximum bending moment that is greater. Would it be possible if I now use the integration part to actually get where the failure mode will occur at the base?
Yeah. I mean, you can do that, but that calculation will be a bit more difficult than just picking, just saying WL squared over 6, and instead of L being 5.4, you put L is equal to 5. This is a lot easier if you did it that way. If you wanted the moment at the place where this wall would actually fail. You understand? Than to do the fancy integration thing, to do the curve and then to do this integration. You still get the same answer, but this other approach would be a lot easier. And as we always seek to find the easiest route to the solution. It's part of what the world wants. The cheaper solution in terms of even effort.
Okay, understood.
Good. Yes, any other question, any other thought, comment? So I will share these notes. I will share these notes with you. Please look at them. If you come across something that you think you want to discuss, even if we've passed it, please, in the next session or in a future session, even if it's not the next session, you can take us back to this topic. Let us discuss your thoughts as well. So thank you very much. Have a good afternoon, and we meet again in the next session. Thank you.